All right, hi guys. I want to talk about using formulas to solve problems. The graphs work great for an overview of what's going on in terms of motion, where it is, how far it's gone, how fast it's going, how that velocity is changing, um, or when that's occurring. But as we start to get situations where it doesn't end at a whole number or it's not as easily seen what the value on a graph is, then they start losing some precision. So if we want to get more precise answers, usually we want to use formulas. The formulas themselves are based on the graphs. So if we look at the formulas that we've gotten from graphs so far, we know, for example, up here, that the slope of a position versus time graph is velocity, average velocity. The slope of a velocity versus time graph is acceleration. We can use those facts and those to generate more formulas. And I want to specifically talk about motion with constant acceleration, because most of the time we deal with any type of acceleration, we're going to deal with constant accelerations. In other words, the slope of the velocity versus time graph stays constant. And we could have to break things up into areas where the velocity is changing in a constant rate. So if you do have a graph that has a changing acceleration, you can only calculate for a given area that the acceleration is constant. And we have here some formulas that work with that. One of the formulas is just a rearrangement of the acceleration definition. If we have a constant acceleration, then we don't have to worry about what a average acceleration is, because the average doesn't change. So this first formula that is on the slide here, v equals v0 plus at, final velocity equals initial velocity plus its acceleration versus time, is just rearranging the acceleration formula, which is oftentimes written as delta v over t. But in this case, of course, delta v is v minus v0. So if we rearrange the acceleration formula to solve for final velocity, this is what we get. That's a great formula to use for situations when you don't know how far something's gone, but you know that it has gone a certain amount of time and a certain acceleration, and you want to know how fast it's going after that, or how fast it started. Remember, we have these different variables that we use. Now, there's 5 different variables that we use in all of our formulas. And those 5 variables are behind me here: displacement, initial velocity, final velocity, and we don't use these subscripts. We use v0 for initial velocity and v for final velocity, or v naught for initial velocity. So then acceleration and time. And some combination of any of those 5 will give us the ability to figure out what's going on at any point in an object's motion. The graph below this formula here is our standard velocity versus time graph. And the nice thing about this is, if we have a constant acceleration, if we compare the initial velocity, v naught, and the final velocity, v, the average is right in between. It's the midpoint of that. So it's the midpoint of time. It's also the midpoint of velocity. So we can use the average velocity there for different purposes. Now, we had an average velocity formula already, and that one works for any situation. That's delta x over delta t. But this one only works with constant acceleration. But if we have a constant acceleration situation, which we most of the time do, we can take those 2 formulas and equal them out. So I have delta x over delta t equals 1/2 v0 plus v. And oftentimes this is rearranged to solve for displacement by multiplying by the time. And we don't use delta in here for time. Okay. Now that gives us the ability to find a displacement if we know the initial velocity, the final velocity, and how long it took between those 2 times. So that is one of these. As you can see, a position is a function of time. So these formulas all work in constant acceleration, but only constant acceleration. So we can find position, and position versus displacement is just x minus x naught. So I usually write it as delta x, but you can write it as x equals x0 plus 1/2 v naught plus b times t. The other one here is position as a function of time. That occurs when we take that the first formula that I mentioned, the rearrangement of acceleration and solve it for final velocity, and we substitute the final velocity into this formula above it. So when we substitute final velocity, which is initial velocity times acceleration, or plus an acceleration times time, we get the next formula here, the x equals x naught plus v0t plus 1/2 at squared. Each of these formulas has a different type of problem it can solve for. Notice, of the 5 variables, each formula has 4 of them. And so the first one there, position as a function of time, does not have acceleration. So if you don't know acceleration or don't need to know acceleration, that's the one to use. The second formula here doesn't have final velocity. So if you don't know final velocity or don't need to know final velocity, that's the formula you want to use. This last formula on the screen here is a formula that doesn't involve time. So it's usually written with that v squared equals v naught squared plus 2a delta x. So we don't worry about the intermediate part there. So if you don't know how long something's moved, but you know how far it's moved and what speed it started at and the acceleration rate, we can figure out what speed it's going at, or we can rearrange it to solve for any of those. So all of these give us the ability to solve for a position or a velocity or an acceleration or time, all right? So keep in mind that when we have an acceleration, it is a predictable curve. So the time will tell us where something is, but these formulas are based on that curve. So it's a squared function. So when we have something that involves time and position, we're going to end up squaring it. So we get a quadratic. All right. These are our formulas that we use. And the bottom 3 are by far the most common ones that we use. But notice each of these involves, and they're all based on our relationship between the graphs and the values on the graphs. And they all have one of the 5 variables that they don't use, the bottom 4 formulas. Actually, all of the formulas. The top formula doesn't have displacement. The second formula is just average velocity, so we don't use that too much, but it's the basis for the rest of them. The third one does not have acceleration. The fourth one does not have final velocity, and the fifth one does not have time. The one thing that they all have is initial velocity. So we don't have a formula necessarily that doesn't have initial velocity. So generally, we're either going to be solving for initial velocity or we're going to need initial velocity for situations. Now, we can substitute, we can rearrange something and substitute for initial velocity to get rid of it, but rarely is that something that we do. All right? So when we have an acceleration, we have the typical curve, and that can predict things. This is what they do to figure out the stopping distance for vehicles, for example, for accidents. We know how fast it's going, we know at what rate it accelerates, and if we know the rate it accelerates, we can figure out how far it goes, and that is also a squared type of function. So we get a different, so you go a lot farther, even if you're accelerating at the same rate negatively, you go a lot farther in the initial time while you come to a stop. So being aware and knowing how the acceleration occurs, you can kind of understand that that first initial reaction is really important. I have here a couple examples to show you guys in how we use this kind of stuff. So if we look at my screen here, Daredevil is trying to jump his motorcycle over a canyon, needs to be moving at least 45 meters per second when he hits the ramp. he has to time it right. So he has 12 seconds, and he wants to be going at that speed. So he's going at 20 meters per second to prepare. He hears the introduction, so he's got 12 seconds. So he needs to know, is he going to be going the right speed by the time he accelerates at a rate of 2.25 meters per second. So here's my variables. I always write out all 5 variables. And then I go through and look and see, what do I have? Well, I have the 45 meters per second. I have the 12 seconds. I have the 20 meters per second, and I have the 2.25 meters per second. But be careful. One of these is not part of the problem. And the one that's not part of the problem is this one, the 45 meters per second. That does not describe his motion. That describes what he needs to do. So what we're really trying to do is solve for final velocity and see if it's above 45 or less than 45. So we have the acceleration, 2.25 meters per second. We have the initial velocity, 20 meters per second. And we have the time, 12 seconds. We don't have the displacement. We don't know how far away he is. We don't need it. We have a formula that does not involve displacement. And that is this one right here. Final velocity is equal to initial velocity plus a times time. So we can use that to find the final velocity, 20 meters per second plus 2.25 meters per second, so meters per second squared, times 12 seconds, right? So this is the 20 meters per second is how fast he would be going if he didn't accelerate, and the a times t is how fast he changes his, or how much his velocity changes. 2.25 times 12, well, 2 times 12 is 24, 0.25 times 12 is 3, so we're looking at 27 meters per second. So 20 meters per second plus 27 meters per second. Now, I don't expect you to show all this work, but I would expect you to show what formula you're using and how you set it up. So that type of information. Remember, we want to communicate how we're thinking through this stuff when we're doing these. So when you take the AP test, the AP graders will be aware of that. So we're going 47 meters per second, which is fast enough. Because he needs to go 45. All right. Let's say that he's landing and he hits the ground at the same speed he landed at, or he left at. So the initial velocity is 45 or 47 meters per second. And he stops in 3 seconds. Final velocity then is 0. The acceleration is unknown, and the displacement is unknown. Okay, but the question is, how far did he travel? So we need to answer that question and do that. Okay, so let's take a look at this, and we can solve for the displacement, but we have to use a formula that doesn't have acceleration. So that's one of the formulas that we did today, and that is this one. Let me get that up. Going here, delta x equals 1/2 v naught plus v times time. All right, because we know initial velocity, we know final velocity is 0, we know time. So we can tell how far he went as he hit the brakes. Final initial velocity is 47 meters. Final velocity is 0. Time is 3 seconds. So our displacement is, well, 1/2 of 3 is 1.5 times 47. What's 47 times 1.5? Okay, so he stops in 70.5 meters as he comes to a stop in 3 seconds. So that's an example of how we use these. We'll have more examples, and obviously your homework has some examples as well. So Keep working on these. Tomorrow or the next video lesson, I'll talk about free fall. Thanks a lot. Bye.